as an eigenvector and eigenvalue of A respectively. So note here that eigenvectors and eigenvalues are tied together, which means that every eigenvector has an associated eigenvalue. We often characterize square matrices in terms of their eigenvectors. One way of looking at eigenvectors is as follows. X can be thought of as a vector in R power n, and the square matrix A acts like an operator which transforms X into another n-dimensional vector Ax. Now, the eigenvectors of A are those vectors which, on being transformed by A or operated upon by A, are only scaled by lambda but not rotated. In other words, their direction does not change. We can have a look at this example here. The 2 cross 2 matrix A, on multiplying the vector x phi 1, gives back the vector x multiplied by the real value 7. So here x is an eigenvector of A and 7 is an eigenvalue of A. We can see that 0 would always be an eigenvector of any matrix if we simply go by the Ax equals lambda x definition. Hence, we only refer to non-zero vectors as eigenvectors. So the question is, given a matrix A, how does one find all the eigenvalue eigenvector pairs? By simplifying Ax equals lambda x, we get A minus lambda I to x equals 0. Now, since we are only looking at non-zero vectors, det of x can't be 0. I mean, x can't be a 0 vector, which means that det of A minus lambda I should be 0. So the equation det of A minus lambda I equals 0 is called a characteristic equation of A. Solving this equation gives us all the eigenvalues of A. One thing you must note is that even though all the values of A are real, A is a real matrix, the eigenvalues can be complex. There are interesting relations between some properties of a matrix and its eigenvalues. For instance, the trace of a matrix is equal to the sum of its eigenvalues, while the determinant is equal to the product. The rank of a matrix is equal to the number of non-zero eigenvalues. Note that if an eigenvalue has multiplicity greater than 1, for instance, if two distinct eigenvectors x1 and x2 both have eigenvalue lambda, we would count lambda twice. Also, we can describe the eigenvalues of A inverse in terms of the eigenvalues of A, provided of course A is invertible. The eigenvalues of A inverse will be of the form 1 by lambda I, where lambda I is an eigenvalue of A. Now let's have a look at an interesting theorem about eigenvalues and eigenvectors. The theorem goes as follows. If a matrix has all its eigenvalues distinct, then its eigenvectors are linearly independent. We shall prove this by what is called a proof by contradiction. If this theorem doesn't hold, that means there's a set of k eigenvectors such that it is linearly dependent. Let the ith vector in this set be Vi and the corresponding eigenvalue be lambda I. Note that we are considering the smallest such set. Since the set is linearly dependent, this means there exists real constants ai such that summation ai vi equal to 0. Now let's multiply both sides of the equation by a minus lambda k times I. Since Vk is an eigenvector of A minus lambda ki Vk will be equal to 0. We can understand this from the characteristic equation. Hence, the term corresponding to Vk disappears from the equation. since it goes to 0. Now for the remaining eigenvalues, since we know they are distinct, the term lambda I minus lambda k cannot be equal to 0. Note that A minus lambda ki into Vi simplifies to lambda I minus lambda k times Vi, since A Vi equals lambda I Vi. However, now we can think of Ai times lambda I minus lambda k as a new constant Bi. This means now that we have a summation running from I equals 1 to I equals k minus 1, such that Vi equal to 0. However, we had assumed that the set of size k was the smallest set of linearly dependent eigenvectors. However, now we have an even smaller set. This contradicts our starting assumption. Hence, such a set of k linearly dependent eigenvectors can't exist for any k greater than equal to 2. Hence, all our eigenvectors are linearly independent. Hence, our theorem stands proved. Diagonalization gives us a way of representing a matrix in terms of its eigenvalues and eigenvectors. Let's consider a n cross n square matrix A. We denote the matrix where every column is an eigenvector of A by S. On multiplying S by A, each column would get multiplied by lambda I, since the column itself is an eigenvector of A. This right-hand side can then be simplified as the product of two matrices, the first one being S itself, while the second one being the diagonal matrix where the ith diagonal element is the eigenvalue lambda I. Remember that the LHS is AS. Now we have the equation AS equals S capital lambda, where capital lambda is the diagonal matrix of eigenvalues. On simplifying this, we get A equals S capital lambda S inverse. This is a diagonalization of A. Note that S inverse AS is a diagonal matrix, since S inverse AS is nothing but capital lambda, the diagonal matrix of eigenvalues. This result is dependent on S being invertible. It will hold if the eigenvalues of a matrix are distinct, since the eigenvectors would then be linearly independent. This would mean the columns of S would be linearly independent, and hence S would be full rank and, as a consequence, invertible. When do we say that a square matrix is diagonalizable? Well, when such a diagonalization exists. We saw that we needed S to be invertible for the diagonalization to exist. Another advantage of diagonalization is that it simplifies the process of computing A bar n. We first represent every A in diagonalized form. Now we can see that the S inverse of the first term and the S of the second term would multiply to give us I. Similarly for the second, third, fourth, and so on. In this way, by regrouping the terms, we get A bar n equal to S capital lambda bar n S inverse. Note that it is very easy to compute the nth power of a diagonal matrix, since you just have to raise every diagonal element to the power of n. In this way, The diagonalization has helped us simplify the process of computing a power n. Without this simplification, we would have needed to multiply a non-diagonal matrix n times. If a matrix is symmetric, then all its eigenvalues are real numbers. Also, its eigenvectors are orthonormal, that is, they are mutually orthogonal and normalized. This means that the matrix of eigenvectors S is also orthogonal. We had seen that for orthogonal matrices the inverse and the transpose are the same. Hence, we can write A equals S capital lambda S transpose as per the diagonalization we defined earlier. For symmetric matrices, their definiteness can be inferred from the signs of their eigenvalues. Suppose that A equals S lambda S transpose. Now, taking the quadratic form with respect to A for a vector x, x transpose Ax simplifies to y transpose capital lambda y, where y is S transpose x. This further simplifies to sum over I lambda I yi square. Now, for a matrix to be positive definite, this term must always be positive. Since yi square is always greater than 0 anyway, the sign of this term depends on the eigenvalues. If all the eigenvalues are positive, the matrix is positive definite. If we know that a matrix is positive semi-definite or PSD, then what can we say about its eigenvalues? Since the quadratic form of a PSD matrix is non-negative for any vector x, this should hold for the eigenvectors too. Now, since Ax equal to lambda x, x transpose Ax simplifies to lambda norm of x square greater than equal to 0. Since eigenvectors are non-zero by definition, the square of the norm is always positive. This means that every eigenvalue of A is non-negative. We learnt about diagonalization, which took in a square matrix of size n cross n and represented it in terms of its eigenvectors. However, we cannot directly apply the same diagonalization for rectangular matrices, since the notion of eigenvector is defined only for a square matrix. We need a diagonalization for rectangular matrices since we encounter them often. For instance, the matrix of n data points or p features, or the matrix of n documents and r terms. For a rectangular matrix A of size m cross n, we can represent it in terms of the eigenvectors of AA transpose and A transpose A, both of which are square matrices. This is known as the singular value decomposition. A is represented as U sigma V transpose, where U is a M cross M matrix, sigma is a M cross N matrix, and V is a N cross N matrix. The three elements U, sigma, and V are as follows. In U, every column represents an eigenvector of AA transpose. In V, every column represents an eigenvector of A transpose A. Sigma is a rectangular diagonal matrix with each element being the square root of an eigenvalue of AA transpose or A transpose A. Now, note that AA transpose and A transpose A have different eigenvectors, but the set of eigenvalues is the same. This is because, suppose A transpose A x equals lambda x. for some eigenvector x and eigenvalue lambda. Now multiplying both sides by a, we get AA transpose times AX equals lambda AX. Hence, AX is an eigenvector of AA transpose while lambda is also an eigenvalue of AA transpose. This is why A transpose and A transpose A have the same set of eigenvalues. The significance of this decomposition is that if we order u, v and sigma such that the eigenvalues whose magnitude is larger come first, both in u and v in the column order and also along the diagonal in sigma, then we can drop everything greater than index r to get a r-dimensional low-rank approximation of the original matrix A. This approximate form of A will be represented as U, which is an M cross R matrix, sigma, which is a R cross R matrix, and V, which is a N cross R matrix. Consider a function f which takes in matrices of dimension m cross n and outputs real numbers. The gradient is the matrix of partial derivatives. The I, jth element of delta f of a, or the gradient of f of a, is the partial derivative of f of a with respect to aij. Consider a different type of function which takes in a n-dimensional vector and returns a real number. The Hessian for this function is defined as follows. The I, jth element of the Hessian is given by first differentiating f of x with respect to the jth component of x, xj, and then the ith component, xi. We can see that the Hessian would be a n cross n matrix. Now let us study how we can find the gradient for some simple vector functions. Consider the function f of x equals b transpose x, where x is an n-dimensional vector and b is also an n-dimensional vector. F of x can be written down as sum over I equals 1 to I equals n bixi. On differentiating this with respect to the kth component of the vector x, we get dou fx by dou xk equals bk. Hence, the gradient of fx is given by the vector b. We can see how this intuitively relates to the first derivative of the scalar function fx equals ax, which is equal to a. We had earlier looked at a type of function called the quadratic form defined for a n cross n matrix A. The quadratic form with respect to matrix A is a function f of x equals x transpose ax, which takes in a n-dimensional vector x. Now let's have a look at how one can find the gradient and Hessian for the quadratic form of a known symmetric matrix A. We can write down f of x as sum over I equals 1 to n sum over j equals 1 to n aij xi xj. We can split up this summation into 4 terms based on whether I and j are equal or not equal to k. Finally, we get dou fx by dou xk equal to twice sum over I equals 1 to I equals n aki xi. Note that the simplification from the second last step to the last step can only be done if A is symmetric. Thus, we get the gradient of x transpose Ax as equal to 2Ax. Similarly, on further differentiating every element of the gradient by xk, we can derive the Hessian of the function. The Hessian of this function comes out to be 2a.